Hey guys, what's up? In our last video, we learned how to visualize our network using TensorBoard, and before that, we learned how to use basic TensorFlow to create basic neural networks like dense, fully connected neurons, and to create an OR gate. So now I think we are pretty much ready to move forward with the advanced networks like convolutional neural network or recurrent neural network. That's why in this tutorial we'll try to create something complex like an image classifier. So let's get started. So this is the code that we used in our last tutorial. If you see here, there are lots of cluttering, and like to create a hidden layer there are we had to use five, how many, 1 2 3 4 5 6 lines, and for input layer we have 3 lines, and like this for optimizer, and like this. So what I want to do here is I want to reduce the number of size like this for one hidden layer. If we take this much lines, then if we are trying to create a huge network with hundreds of layers, let's say, the number of lines will be too much, and it will be very much difficult for us to debug the code if there is any error. So what we are going to do here, we are going to create our own network builder class, which we will be using to create our network. So that will look like something like this. Let's create a new project, or let's create a file here only. New file. I'm going to call it network builder, and network builder, and in this we are going to import our TensorFlow library. Import TensorFlow as tf. Now we are going to create the class name, we'll name it network builder, and this is the object initializer. For now we are not going to do anything here, but we'll keep that so that we can add some more things later. So what will be inside the network builder? What we are going to do here is we are going to abstract everything, like all this hidden layer, input layer, and there are more layers like that for image classifier, like convolutional layer, pooling layer, activation layer. All these things will put us different functions, so that will only supply the last layer of the network, and the network builder will automatically attach a new layer on top of it. For that, let's create those methods. I'm going to first one will create a convolutional layer attacher. So attach conv layer and pass, let's copy it, paste. So we want convolutional, we want a pooling layer, we want a flattened layer, we want a dense layer, we want a few activation, let's say 1 2 3 3 activation layer, and that's it for now. Let's just change the name, pooling layer, flatten layer, dense layer, ReLU, softmax, and sigmoid. So we'll create each and every layer, and I will also tell you what are these layer and what each and every layer does as we write the code for each of this method. Let's add attach conv layer. Okay, so before starting the conv layer, let's talk about what is a conv layer. So a convolution layer, what it does, so let's say this is an image. So what a convolution layer does, it creates some patches which we call kernels. So let's say this is a patch, what it does, and it has some shape. First let's say it has some shape like this, or we can call it features. Let's group it. So let's say this is our patch, which is nothing but a, small image. What convolution layer does, it takes that patch or kernel and it will slide that kernel over the actual image, and it will try to find a match between the patch and the actual image. So in this case there is no almost zero match. So as we move this kernel over the actual original image, tries to find the match and puts the matching percentage in another image, another blank image. So let's say for initially this is the patch was here, so it tries to find the match and that value will be written here for each and every pixels. uh, so it will move one pixel and it will write the value in the next pixel. It will move one pixel and it will write the value in the next pixel in this new image. So this is the original image, this is the feature kernel, and this is the feature map that is generated by sliding the kernel over the original image. So when we are creating a convolution layer, it is creating, let's say, 10 or 20 kernels, 20 different kernels which has different features, and trying to extract those features in the original image and creating the feature map from that. And looking at the feature map, we can tell what are the features and which position that feature is placed. So that is how what convolution layer is. So let's create a convolutional layer. So to create a convolution layer, we need input layer on which we will apply the convolution. So this is the previous layer where we will attach the convolution layer, not the initial beginning of the layer like input layer. This input layer means the input for the convolution layer, which is the previous layer. Now we will add an output size. By default I'm giving it 32. So this is output size is the number of feature map that we want to generate. So number of feature map is equal to the number of kernels. So if we want 32 outputs, so we have to have 32 kernels to get 32 outputs. Now we also have to define let's full screen it. So we also have to define the size of the kernel. So feature size, and it's a two-dimensional. Let's set the default value to 5 cross 5, and another parameter, that is strides, equals. So there are four dimensions. One is batch size, one is width, one is height, one is the channel. And this stride parameter, what it decides means each and every direction of this dimension, how many pixels this kernel will move to create the feature map. If we set 2 for the width and height, it will move every time it slides the feature map, it will move twice. Means it will move 2 pixel left and 2 pixel down. So first it will go like this, then after reaching here, it will come here and it will Again it will come in the beginning and it will go 2 pixel down, calculate the match. Again it will go 2 pixel like this, and again it will come here, and again it will go initial position, horizontal initial position, it will go 2 pixel down, and again it will calculate like this. So this way it will calculate the create the entire feature map. And in the stride will decide steps. So we don't want it to skip any images in the bulk dimension, so that it goes each and every images in the bulk. So it will be 1, and we can set this to 2, and we don't want to skip any channels. We want to want it to analyze each and every channels, so it will be also 1. So it will it will not skip any channel. And for the height and width, this we can decide. We can even make it 2, so it will every 2 pixel it will move into height and width dimension. And we can also make it 1, which will make it will crawl each and every pixels. Now that we have all the inputs that we need, let's create the convolution layer. So to create the convolution layer, we have to know what is the size of the previous layer or the input layer. Now that we have the input layer, we can extract the size from the input layer using the getSize method of the input layer. So let's create a variable input size equals input layer dot get it is shape as list. So we want it to be as list, so that we can apply regular Python syntax in that. To attach the convolution layer, we only need to know the number of channels that is available in the previous layer. So for input for our image layer, where we supply the input, the channel is 3 if in case of a color image, and channel is 1 in case of if it's a grayscale image. But let's say we are applying this convolution layer on top of another convolution layer, and this convolution layer is supplying creating 32 feature maps, or let's say 20 feature maps. So the 20 feature maps will all those feature maps will stack together and create a channel. So the input for the second convolution layer will have 20 channels as an input image. We have to know the channel number based on the input. We cannot hard code it like 3 or 2. So for that, we'll get the shape of the input, we'll get it as list, and we want to know what is the number of channel. So we can get it like the last one will be the number of channel, which is this one. So we can get it like -1 will give us the last one. Now that we have the input size, which is the input channels, we have the output channels, we have the feature size. Now we can create the kernels, or the weights for the kernels. So we will create the weights, conv weights equals tf dot variable, and here we will supply tf dot random normal. We'll initialize it as a random normal, and the shape will be the first the feature dimension, this kernel dimension. So it will be inside a dimension. We have to supply the shape first. So the shape will be first the feature size, which is first one, feature size second one. Now the input size, and output size. We can also supply the standard deviation and all, but I think the default ones will work fine. Now the next thing that I want to do here is provide a name. Let's give it a name, and let's put it in the next line. Let's provide a name like conv weights. So so this name will come in the tensor board when we will display this. So we have our convolutional weight. We have to create the bias. Conv bias equals tf dot variable tf dot random normal, and we have to give the shape, where the shape is only the output size. Another thing, let's name it for tensor board, which is conv. We can give any name. So we have our conv weights, we have our conv bias. Now we can create a conv layer. Conv layer equals tf dot nn dot conv 2d. So we have to supply the filters. Filters are nothing but our weights for the convolution, and before that we have to supply the input. The input is the input layer, comma conv weight is the filters, strides is the strides from the parameters, padding. Okay, so padding is something, let's say we are creating a feature map from sliding the kernel. If you can see, this entire region's score will be placed in this pixel, in the first pixel. So it will move in the second pixel, and it will be placed in the second pixel. So this way, if we move till this point, this entire region's pixel will be placed at the last of this pixel. So if the image has 100 pixel width, then you will have little bit less than the 100, because you are starting from this position. You are starting from this position, not at the you are not starting from at this position and going like this. So then it will be like total 100, and you have to end here. But what you are doing, you are starting from the middle. Like you are starting from this position, where the entire thing is it's already, this edge is already after a few pixels later, and you are ending here. You are not going till this point. Then it will be 100, let's say the full width. So the output feature image will have little bit less size than the input feature map or input image. But this will create some issues for us, because the images are shrinking down, and we don't have enough pixel to move forward to stack more layers. If there is let's say it shrink down to 1 pixel, then we cannot do more processing on that. So what we do to keep the size same, we attach zeros at the end where there is no data we have for the feature map. So that is called padding. So if we want to pad, then we can have like a padding, let's name it, and we can set it same. Then what will happen, if we set the padding as same, then it will keep the dimension or the size of the output feature maps, and the input feature maps are same. So we'll supply this variable here, padding. Now if we want to change the padding during our network creation, we can just replace supply any parameter here. Otherwise the default parameter it will take, which is same. Now we have our convolutional layer. Let's put it below. And one more thing I want to add, which is a boolean variable called summary. Why I'll put it as a false? Because why I want to add it, because we will set it as true if we want to show this show the values of this variable of this layer in our tensor board. So if we want to see the weights or a histogram of this weights in a tensor board, we will set this summary variable as true. So one last thing what we will do is if summary if summary equals true, or if summary same thing, then tf dot summary histogram, we have to give the name, so it will be conv weights dot name, so it will automatically get the whatever name it has been assigned, which is this one. So we want to get the exact name what is there in the runtime, so we can get it like this. And tf and next we have to supply the value, which is conv weights. That's it for the summary. Now what we will do, we'll return this convolutional layer, and we are done with this attach conv layer function. We'll remove the pass. Just one teeny weeny thing is I want to add a name also, conv layer, and that's it. So we have our convolutional layer. We'll use the same method every time we want to attach a new convolution layer to our network.